Picture this standing on a windswept plain under a sky so thick with stars, it feels like you could reach up and touch them. There are no ticking clocks, no glowing screens, no calendars counting down the days. Just you, the earth beneath your feet, and the endless dance of the sun, moon, and stars above. This was the reality for our ancestors, who looked to the heavens not just for wonder, but for survival. Every sunrise, every shift in the seasons, every phase of the moon held life or death meaning. And from that primal connection to the cosmos, humanity's first clocks and calendars were born not from gears and numbers, but from shadows, stones, and the patient observation of the sky itself. Think about how deeply time shapes our lives today. We wake to alarms, schedule our days in minute-by-minute increments, and measure our lives in years and decades. But long before smartphones or even sundials, ancient cultures found astonishingly precise ways to track time's passage. They built towering obelisks that cast knife-sharp shadows across the desert, marking the hours with nothing but sunlight and geometry. They arranged massive stones into circles and rows, creating ancient observatories that could predict solstices and eclipses with uncanny accuracy. These weren't just practical tools, they were acts of reverence, attempts to grasp something as vast and mysterious as eternity itself. So why does this ancient quest to measure time still captivate us? Because it's a story of human ingenuity, of curiosity triumphing over limitation. Every modern clock, every calendar on your wall, carries echoes of those first stargazers who dared to ask, how can we understand time? In this journey, we'll uncover how civilizations from Babylon to the Andes turned the rhythms of nature into the first systems of time-keeping, systems so enduring that their legacy lives on in the way we structure our world today. From the pyramids to the stars, this is the story of how humanity learned to measure the immeasurable. And trust me, by the end, you'll never look at a sunrise or your wristwatch the same way again. Long before the first cities rose or the first words were written, our ancestors were already keeping time not with gears or numbers, but with the rhythms of nature itself. Imagine a hunter-gatherer 30,000 years ago, etching notches onto a bone under the glow of a campfire. Recent discoveries, like the famous Ishango bone found in Africa, show markings that may have recorded lunar cycles, proving that even in prehistory, humans were obsessed with time's passage. These early timekeepers weren't just tracking days, they were mapping survival. A full moon might mean safer nighttime hunting, while the first frost signaled migrating herds. But the real revolution came when humans stopped wandering and put down roots. Farming changed everything. Suddenly, knowing when to plant seeds or harvest crops wasn't just helpful, it meant life or starvation. Early agricultural societies from Mesopotamia to the Americas noticed patterns. Certain stars appeared when the rivers flooded, or the sun's shadow lengthened as winter approached. They began marking these events with standing stones, notched sticks, or even cave paintings. In France's Lascaux caves, overlapping animal drawings might represent seasonal migrations, a prehistoric farmer's almanac painted in ochre and charcoal. What's astonishing is how precise these early systems became without any modern tools. Take the Warrenfield calendar in Scotland, a series of 12 pits dug by Mesolithic people over 10,000 years ago. These pits align with the midwinter sunrise, creating a rudimentary lunar calendar that tracked months with eerie accuracy. Or consider the Aboriginal Australians, who used the changing positions of constellations to predict seasonal shifts down to the week. These weren't crude guesses, they were the result of generations of careful observation, passed down through stories and songs. This primal connection between time and survival still echoes in our language today. The word month comes from moon, and year shares roots with ancient words for harvest. Every time we glance at a calendar or check our watches, we're using systems born from that ancient dance between human ingenuity and the natural world. The next time you see the moon hanging low in the sky, remember, you're looking at humanity's first clock, one that's been ticking for millennia. Rising from the Salisbury Plain like a frozen choir of giants, Stonehenge has whispered its secrets across 4,000 years. But this wasn't just a monument, it was a celestial calculator carved in stone. Picture the summer solstice dawn, when the first golden light slips perfectly between the towering heel stone to strike the altar at the center. That precise alignment wasn't luck, it was genius. The builders didn't just stack rocks, they engineered a horizon-scale sundial that could pin down the year's turning points with breathtaking accuracy. What's truly staggering is how they did it without writing, wheels, or metal tools. Modern laser surveys reveal that some stones were shaped to account for optical distortion, like prehistoric astronomers correcting for atmospheric refraction. The outer circle's lintels curve slightly, creating a level surface despite the uneven ground, proving these Neolithic engineers understood concepts we'd now call spherical geometry. And those famous station stones forming a rectangle, they frame key moonrises during the lunar standstill, an 18.6-year cycle few modern observers could identify without software. But Stonehenge wasn't alone in this cosmic conversation. Across the channel, the Karnak stones in France stretch for miles like a petrified army, their rows aligning with both solar and lunar events. In Egypt's Nabta Playa, a stone circle older than Stonehenge by 2 millennia, tracked the summer solstice using stones no taller than a man's knee, proof that precision didn't require scale. What unites these sites isn't just their alignments, but their purpose. They weren't cold observatories, they were sacred spaces where timekeeping blended with ceremony. The bones of feasted animals found at Stonehenge suggest solstice gatherings where the sky's rhythms dictated when to plant, when to marry, when to pray. Perhaps most haunting is how these builders encoded warnings in stone. The same alignments that marked the life-giving solstices could also predict eclipses, events often seen as cosmic omens. By tracking the Saros cycle, where eclipses repeat every 18 years, they might have viewed these celestial disturbances not as chaos, but as part of time's grand pattern. That shift from fearing the unknown to mapping its rhythms marks one of humanity's greatest leaps. When you stand in Stonehenge's shadow today, you're not just seeing a relic. You're witnessing the moment we began to tame eternity itself by reading its signature in sunlight and stone. While Stonehenge's stones whispered secrets to the sky along the Nile, the Egyptians were perfecting timekeeping in a way that would echo through millennia. Picture the banks of the river at dawn, where towering obelisks stretch toward the heavens, their shadows creeping like silent fingers across the sand. These weren't just monuments, they were the world's first shadow clocks, turning sunlight into a measurable rhythm. By 1500 BCE, Egyptian astronomers had carved notches into stone slabs, marking the shadow's path to divide the day into 12 equal parts. Imagine the precision, no gears, no electricity, just the sun's unwavering arc and human ingenuity. But why did the Egyptians need such accuracy? The answer lies in the Nile's life-giving floods. When the river swelled, it left behind fertile silt, but only if farmers planted at exactly the right time. Too early, and seedlings would drown; too late, and the soil would bake dry. To solve this, they didn't just track hours, they reinvented the year itself. By observing Sirius, the brightest star, they noticed its annual rising just before dawn coincided with the floods. This celestial clue led to the creation of a 365-day solar calendar, a revolutionary leap that sliced the year into 12 months of 30 days plus 5 sacred days. For the first time in history, time wasn't just observed, it was systematized. The elegance of their design still astonishes. Take the Merkit, a simple tool made of a palm rib and plumb line, used to align structures with the stars. Priests would wait for specific constellations to cross the Merkit's line, marking midnight with uncanny precision. Or consider the water clocks found in tombs, where dripping liquid measured hours through the night, a solution for when the sun's shadows vanished. These weren't just tools, they were bridges between Earth and cosmos, ensuring temples opened their gates at the exact moment prayers were believed to reach the gods. What's often overlooked is how deeply timekeeping intertwined with spirituality. The sundial's shadow wasn't just a marker, it was the finger of the sun god Ra, tracing his journey across the sky. Even their word for hour, WNWT, meant to watch or to guard, linking time with divine vigilance. When we glance at our watches today, we're heirs to that sacred legacy. The next time you check the clock, remember, those ticking seconds began as shadows on the sands of the Nile, where humans first tried to catch eternity in a sundial sweep. While the Egyptians measured time through shadows and floods, the Babylonians took a radically different approach. They turned the sky into a mathematical masterpiece. Picture scholars in ancient Mesopotamia crouched over clay tablets under the stars, scratching precise symbols with reed styluses. These weren't just records, they were the birth certificates of modern timekeeping. The Babylonians didn't merely observe the heavens, they dissected them with numbers, creating the first known mathematical framework for time, their greatest legacy. The system that still ticks inside your watch today, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. Why 60? The answer lies in the elegance of their sexagesimal system. Unlike our base 10 counting, which uses fingers as a natural guide, base 60 offered something extraordinary: divisibility. 60 can be split evenly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, making calculations smoother than the Nile's currents. This wasn't just convenient, it was revolutionary. Imagine trying to divide an hour into thirds with a base 10 system. You'd end up with clumsy decimals. But with 60, 20 minutes falls perfectly into place. The Babylonians' choice was so practical that millennia later, we still measure angles, geographic coordinates, and even pixels in digital displays using their logic. Their astronomical precision was equally groundbreaking. Babylon's scholars tracked Venus with such accuracy that their observations, etched into cuneiform tablets, still match modern retrocalculations. They compiled star catalogs, predicted eclipses, and even identified the repeating cycles of lunar eclipses known as the Saros cycle, all without telescopes. One tablet, now called the Astronomical Diary, records celestial events alongside historical happenings, proving they saw time as both a cosmic rhythm and a human story. When a lunar eclipse darkened the sky, they didn't just note it, they linked it to the fate of kings, believing the heavens mirrored earthly events. What's often overlooked is how deeply their work influenced later cultures. The Greeks borrowed their star maps, medieval Islamic astronomers built upon their calculations, and Renaissance scholars pored over translated Babylonian texts. Even today, when you set an alarm or catch a flight, you're relying on a system refined by Mesopotamian minds who gazed at the same stars we do, but saw in them a numerical harmony we've never improved upon. The next time you count down the seconds, remember, you're not just watching time pass, you're reading a 4,000-year-old equation written in the language of the cosmos itself. While the Babylonians counted in 60s and the Egyptians tracked the Nile's floods across the Atlantic, the Maya were engineering a calendar so precise it could map cosmic time down to the day for millions of years. Imagine a civilization without telescopes or metal tools, yet one that calculated Venus's orbit to within 2 hours of modern astronomy's measurements. The Maya didn't just mark time, they wove it into a tapestry of interlocking cycles where celestial events dictated everything from crop planting to the fate of kings. At the heart of their system lay not one, but 3 calendars operating simultaneously, each with its own sacred purpose. Take the Tzolk'in, a 260-day cycle that functioned like a divine clock. Unlike our linear months, this calendar paired 20-day names with 13 numbers, creating a rhythmic dance where each day carried unique spiritual weight. A priest might consult it to determine auspicious dates for battles or marriages, believing certain combinations held cosmic power. Then there was the Hob, a 365-day solar calendar divided into 18 months of 20 days, plus 5 unlucky days called Wayeb. Farmers relied on its precision when the Hob signaled the arrival of spring rains. Entire cities moved in unison to plant maize. But the true marvel was how these 2 calendars synchronized. Every 52 years, the Tzolk'in and Hob would realign like celestial gears, marking a calendar round so significant that the Maya extinguished old fires and lit new ones in celebration, symbolizing time's renewal. Yet even this wasn't ambitious enough for Mayan astronomers. Their long count calendar stretched across millennia, counting days from a mythical starting point in August 3114 BCE. Unlike Western calendars that reset yearly, the long count rolled forward in nested cycles. 20 days made a uinal, 18 uinals a ton about a year, 20 tons a katon, and 20 katons a bakton, roughly 394 of our years. This system could pinpoint any date within a span of thousands of years with unerring accuracy. When December 21, 2012 sparked global fascination and misplaced doomsday fears, it was simply the day the long count completed a full cycle of 13 baktons, a cosmic page turn, not an apocalypse. What's truly staggering is how they achieved such precision. At sites like Capon, astronomers carved pecked crosses into stone floors grids that functioned as solar observatories. By tracking where sunlight fell through temple doorways during equinoxes, they corrected their calendars to within minutes per year. Their Dresden Codex, a bark paper book, contains tables predicting lunar eclipses and Venus's movements centuries in advance. One table even accounts for Venus's irregular orbit by subtracting fractions of a day, a correction European astronomers wouldn't master for another 1,000 years. For the Maya, time wasn't a straight line. It was a spiral where history repeated in sacred patterns. Kings ascended thrones on dates mirroring their ancestors' triumphs, and celestial events like Mars's retrograde motion signaled divine messages. When we rush through our digital schedules today, it's worth pausing to consider their vision, a universe where every tick of the cosmic clock held meaning, and humanity's story was written not just in years, but in the dance of planets and stars. While the Maya tracked celestial cycles and the Babylonians mapped the heavens with mathematics, ancient China mastered time through something far more fluid: water itself. Picture a bronze vessel in the Tang Dynasty's imperial observatory, its surface etched with precise markings as a thin stream dripped steadily from one chamber to another. This was no simple timer, it was a clepsydra or water thief, a device so accurate it could measure the hours of the night with unerring consistency, even when the stars were hidden by clouds. What made these water clocks revolutionary wasn't just their function, but their philosophy. To the Chinese, time wasn't a series of rigid ticks, it flowed like a river, harmonizing with the natural balance of yin and yang. The clepsydra embodied this idea perfectly. As water descended from an upper vessel to a lower one, floating indicators marked the passing hours on a scale, often shaped like a celestial ruler. By the Song dynasty, artisans had refined them into intricate masterpieces, some towering over 10 feet tall, with multiple tiers and overflow channels to maintain constant pressure. Imagine the precision. A 9th century clepsydra in the palace of Emperor Xuanzong could divide a day into 100 equal qi, each roughly 14.4 modern minutes, ensuring rituals began at the exact auspicious moment. But these weren't just ceremonial ornaments. Water clocks shaped history. Military strategists used portable versions to coordinate nighttime attacks, while astronomers relied on them to record celestial events down to the quarter hour. One Tang dynasty text describes how officials synchronized water clocks across cities by observing the shadow lengths of standardized poles, an early attempt at standardized timekeeping. The real breakthrough came with the addition of mechanical escapements, pioneered by the polymath Yi Xing in the 8th century. His invention used a weighted chain to regulate the water's flow, a principle later adapted in European pendulum clocks. For the first time, technology didn't just measure time, it controlled its rhythm. What's often overlooked is how deeply these devices intertwined with daily life. Court poets wrote of clepsydras dripping like the tears of the moon, while physicians timed acupuncture treatments by their flow. Even the design reflected cosmic order. The 4 supporting pillars of many clocks symbolized the seasons, and the circular basins mirrored the heavens. When you glance at your smartphone's clock today, you're seeing the distant echo of an idea born in China's workshops. That time, like water, is a force to be channeled, harnessed, and ultimately understood. Beneath the waves off the coast of a tiny Greek island, a corroded lump of bronze lay hidden for 2,000 years until a storm in 1901 revealed what might be antiquity's greatest technological marvel. When divers first pulled the Antikythera Mechanism from that shipwreck, they had no idea they'd recovered a device so advanced it would rewrite history. Roughly the size of a shoebox, this intricate clockwork machine wasn't just a tool. It was a miniature cosmos of interlocking gears, capable of predicting eclipses, tracking planetary movements, and even counting down to the next Olympic Games with astonishing accuracy. What makes this artifact so revolutionary is how it bridges 2 worlds. On one hand, it embodies the Greek obsession with celestial order, the same drive that led Ptolemy to map the stars and Aristarchus to propose a sun-centered universe centuries before Copernicus. But unlike passive star charts, the Antikythera Mechanism didn't just describe the heavens, it simulated them. Turn its hand crank, and 37 precisely cut bronze gears whirred into motion, moving dials that displayed the moon's phase, the sun's position in the zodiac, and the erratic dance of planets like Mercury and Venus. Modern CT scans reveal inscriptions explaining eclipse predictions down to the hour, color-coded by likelihood, a level of detail that wouldn't reappear in European astronomy until the Renaissance. The craftsmanship defies belief. Microscopic examination shows gear teeth cut to within a fraction of a millimeter, some featuring subtle offsets to account for celestial quirks. One gear even models the moon's elliptical orbit using a pin and slot mechanism that mimics the physics of gravitational pull. This wasn't just engineering, it was poetry in bronze, a mechanical ode to the Greeks' conviction that the universe ran on mathematical principles. Perhaps most haunting is what the mechanism suggests about lost knowledge. Cicero wrote of similar devices built by Archimedes, and recent discoveries hint that such machines may have been more common than we thought. A fragment recovered from a Roman-era shipwreck near Crete bears gear patterns eerily reminiscent of the Antikythera system. If these were mass-produced even for elite scholars, it implies an ancient technological tradition we've barely glimpsed. When you watch the eclipse predictions of a modern planetarium show, you're seeing the direct descendant of that salt-crusted bronze box. The Antikythera Mechanism proves that the quest to mechanize time didn't start with medieval clock towers or Swiss watches. It began when a Greek artisan, 2 millennia ago, dared to build a universe inside a handful of gears. Imagine a calendar so out of sync with the seasons that midwinter festivals began falling in autumn, and harvest celebrations arrived as seeds were being planted. That was the reality of early Rome, where timekeeping was less a science and more a political bargaining chip. The original Roman calendar, attributed to the mythical king Romulus, had just 10 months beginning in March and ending in December, with a nameless winter gap treated as a timeless void. Even after 2 extra months were added, the system relied on lunar cycles that drifted steadily out of step with the solar year, requiring priests to periodically insert entire, intercalary months to realign civic life with the seasons. Julius Caesar changed everything during his time in Egypt, where he witnessed the precision of the solar-based Egyptian calendar. Returning to Rome in 45 BCE, he enlisted the astronomer Sosigenes to overhaul time itself. The resulting Julian calendar didn't just tweak the system, it severed ties with lunar reckoning entirely, establishing a 365-day year with a leap day added every 4 years. The math was elegant. By accounting for that extra quarter day in Earth's orbit, the calendar would drift only 1 day every 128 years. Overnight, January 1st became the year's fixed starting point, and the chaotic intercalations that had let politicians extend their terms or delay elections vanished. But the real genius lay in how Caesar sold the reform, by naming the 7th month, July, after himself and later adding August for Emperor Augustus. He turned timekeeping into imperial propaganda. Even the tinkering with month lengths, July and August both getting 31 days to equal Caesar's namesake, showed how calendars could reinforce power. Yet for all its political motives, the system worked astonishingly well. When the Gregorian calendar refined it in 1582, the adjustment needed was just 10 days, a testament to Roman engineering of time. What often goes unspoken is how deeply this reform shaped daily life. Farmers could now plant by fixed dates rather than watching for erratic priestly proclamations. Tax collectors no longer argued over when the fiscal year ended. The very word calendar comes from the Latin calendi, the first day of each month when debts were due, proof that standardized time was as much about money as astronomy. Today, when you scribble a meeting in your planner or count down to New Year's Eve, you're participating in a system forged not just by stargazers, but by senators and emperors who understood that controlling time meant controlling an empire. In the quiet glow of an Abbasid observatory, an astronomer bends over a brass disc no larger than his palm, its surface etched with delicate curves and Arabic numerals. This is the astrolabe, a device so elegant it could map the heavens, tell time by night or day, and even determine the exact moment for prayer, all while fitting in a traveler's pouch. During Islam's Golden Age, while Europe lingered in its so-called Dark Ages, scholars from Baghdad to Cordoba were revolutionizing timekeeping with instruments like these, blending art, science, and faith into tools of astonishing precision. The astrolabe's genius lay in its layers. Picture a series of stacked brass plates, each representing a different latitude with a rotating retere, a pierced star chart spinning atop them like a celestial spiderweb. By aligning the retere with the sun or a known star, users could calculate everything from the hour to the Qibla, the direction of Mecca. But this wasn't just a calculator, it was a portable cosmos. Some astrolabes featured over 40 functions, from predicting sunrise to adjusting for refraction near the horizon. The 10th century scholar al-Sufi didn't just refine the design, he wrote entire manuals on its use, ensuring even students could grasp its celestial mechanics. What's often overlooked is how these devices transcended science. For farmers, astrolabes marked planting seasons by the heliacal rising of Sirius. For sailors, they guided ships across the trackless Indian Ocean. And for devout Muslims, they solved a practical dilemma: how to pray 5 times daily at astronomically defined moments when shadows or stars shifted with the seasons. The astrolabe became a bridge between earthly life and divine order, its brass limbs pointing as surely to Allah's precision as to the next prayer call. Yet the contributions went far beyond instruments. Take al-Batani, whose 9th century measurements of the solar year were accurate to within 2 minutes of modern values. Or al-Biruni, who calculated Earth's circumference with an error margin of just 1% centuries before Columbus sailed. Their secret, a relentless drive to test ancient knowledge rather than merely preserve it. When Ptolemy's star coordinates drifted out of alignment, they didn't blame the cosmos, they rebuilt the models, compiling star catalogues so detailed they'd guide Renaissance astronomers like Copernicus. Perhaps the most poignant legacy lies in the names we still use today. Zenith, azimuth, and even algebra all stem from Arabic terms coined by these scholars. The very word astrolabe whispers of their influence. Greek astron, star, filtered through Arabic al-asturlab. When you check a weather app for sunset times or glance at a compass, you're touching the far edge of a tradition that kept time not just with gears and numbers, but with the conviction that understanding the heavens was a sacred duty. In an age when clocks were rare and calendars inconsistent, these astronomers handed us something timeless, the proof that curiosity, when paired with rigor, could measure even the infinite. Deep within the stone walls of a medieval monastery, the rhythmic chanting of monks marked not just moments of prayer, but the very pulse of time itself. Long before factory whistles or punch clocks, these religious communities lived by the divine office, a sacred schedule dividing each day into 8 canonical hours, from the pre-dawn matins to the twilight compline. But keeping these celestial appointments required more than devotion. It demanded innovation. When the sun hid behind winter clouds or fog veiled the stars, simple sundials became useless. So monks turned to water clocks and candle clocks, marking hours by drips or wax until a revolutionary invention changed everything: the mechanical clock. The breakthrough came with the escapement mechanism, a clever device that transformed continuous force into measured ticks. Picture a toothed wheel caught in a dance with 2 small paddles. Each swing of a pendulum allows the wheel to advance 1 tooth, then stops it abruptly. This tick-tock wasn't just noise, it was the sound of time itself being harnessed. By the late 13th century, monasteries like St. Albans in England housed towering mechanical clocks that used falling weights to power these escapements, their gears synchronized to ring bells for each canonical hour. Suddenly, prayer could be precise down to the minute, day or night, sun or snow. What's often forgotten is how these clocks transcended their religious roots. As their chimes echoed beyond cloister walls, townspeople began organizing their lives around the same rhythms. The word clock comes from the Latin clocca, meaning bell, a reminder that timekeeping spread through sound before sight. By the 14th century, civic towers in places like Strasbourg and Prague boasted astronomical clocks so elaborate they displayed zodiac signs, moon phases, and even processions of apostle statues at noon. These weren't just tools, they were symbols of a new idea that time belonged not just to God but to everyone. yet the monastic legacy endured in unexpected ways. The modern 9-to-5 workday, it mirrors the monk's balanced cycle of prayer, labor, and rest. The punctuality we now take for granted, it grew from an era when missing Vespers was a spiritual crisis. Even the mechanical clock's design, with its gears and escapements, laid the groundwork for everything from pocket watches to supercomputers. The next time you check your phone for the time, remember, those digits trace back to medieval monks who believed that by measuring hours they were touching the divine. Galileo Galilei wasn't thinking about clocks when he first noticed the chandelier swaying in Pisa's cathedral. Like so many breakthroughs in science, his epiphany came from ordinary observation. The way that bronze fixture, disturbed by a servant's touch, swung back and forth with mesmerizing consistency. What fascinated him wasn't the motion itself, but its secret. No matter how wide or narrow the arc, each swing took precisely the same amount of time. This simple truth that a pendulum's period depends only on its length, not its amplitude, would crack open a new era in humanity's relationship with time. Christian Huygens, the Dutch polymath, transformed Galileo's observation into something revolutionary. In 1656, he patented the first pendulum clock, a device so precise it reduced daily timekeeping errors from 15 minutes to under 15 seconds. Imagine the shock of that leap, a world where clocks had previously drifted by hours now corrected to within moments. Huygens' design was elegantly simple. A swinging pendulum regulated the escape wheel's motion, releasing one tooth at a time with each measured swing. The ticking wasn't just sound, it was the heartbeat of a new scientific age. The ripple effects were profound. Suddenly, astronomers could time celestial events to the second, sailors could determine longitude with unprecedented accuracy, and cities could synchronize their rhythms. Before pendulum clocks, noon might vary by minutes between adjacent towns. Now, public clocks could be calibrated to a shared standard. Huygens himself refined the design further, inventing the spiral hairspring for portable timepieces, a breakthrough that would eventually shrink clocks from towering hall fixtures to pocket-sized companions. But the pendulum's legacy goes deeper than mechanics. It embodied a radical shift in how humans perceived time, not as something fluid and subjective, but as a universal constant that could be dissected and measured. When Isaac Newton later formulated his laws of motion, he built upon this very idea that the universe operated with clockwork regularity. The pendulum clock didn't just tell time, it proved that time itself could be tamed by mathematics. What's often overlooked is how these devices shaped daily life. Factories adopted shift work timed to the minute, postal services scheduled deliveries by the hour, and even meal times became fixed events rather than responses to hunger. The pendulum didn't just synchronize clocks, it synchronized humanity, knitting scattered lives into a shared temporal fabric. Today, when your smartphone automatically adjusts to atomic time, it's standing on the shoulders of a 17th century genius who saw eternity in a swinging lamp. Picture this: a British warship in 1741, its crew starving and riddled with scurvy after months lost at sea. They'd sailed westward from England, confident their course would lead them to the Caribbean. But without knowing their longitude, their east-west position, they'd missed their target by hundreds of miles, landing instead on the rocky shores of Portugal. Tragedies like this weren't rare. For centuries, sailors could calculate latitude easily by measuring the sun's height, but longitude remained a deadly guessing game. A single degree of error meant sailing 60 nautical miles off course, enough to strand ships on reefs or leave them circling endlessly in open ocean. The problem was so dire that in 1714, Britain's Parliament offered a fortune, £20,000 worth millions today, to anyone who could solve it. Enter John Harrison, a self-taught clockmaker from Yorkshire who'd spent years obsessing over time's minutiae in his workshop. While astronomers searched the stars for answers, Harrison took a radically different approach. If sailors could compare local noon when the sun peaked with the exact time at a fixed point like Greenwich, the time difference would reveal their longitude. 15 minutes fast or slow translated to 3.75 degrees east or west, simple math, but impossible without a clock that could survive tempests, humidity, and a ship's violent motions. Existing pendulum clocks failed spectacularly at sea, their mechanisms thrown into chaos by rolling waves. Harrison's breakthrough came in 1735 with his first marine chronometer, H1. Instead of pendulums, it used paired balance springs that countered each other's errors, along with wooden components resistant to rust. But his masterpiece, H4, completed in 1759, was a pocket-sized marvel. Its high-frequency balance wheel, lubricated with diamond dust, lost just 5 seconds over 81 days at sea, a feat akin to throwing a watch into a hurricane and having it keep perfect time. When Captain James Cook took Harrison's design on his second voyage, his charts of the Pacific were so accurate that modern GPS coordinates still align with them. The economic ripple was staggering. With precise navigation, voyages that once took months due to course corrections could now plot straight lines across oceans. Insurance costs for cargo ships plummeted, trade routes expanded exponentially, and empires redrew their maps with newfound confidence. The chronometer didn't just save lives, it powered the first wave of globalization, linking continents with threads of measured time. Yet Harrison's victory was bittersweet. Parliament withheld his full prize money for decades, demanding further tests and modifications. Only intervention by King George III secured his payment in 1773, 3 years before his death. Today, his original chronometers tick quietly in London's Royal Museum's Greenwich, their polished brass hiding the truth. These weren't just clocks, they were the keys that unlocked the world. As factory whistles screamed across soot-blackened cities and steam engines crisscrossed continents, time itself was being reforged in the fires of industry. Before the 19th century, noon in London might differ by 20 minutes from Bristol, just 100 miles west, each town setting clocks by the sun's local position. But when railroads began stitching nations together, this patchwork of local times became dangerous chaos. Trains hurtling toward each other on single tracks needed precision scheduling to avoid disasters, while factory owners demanded synchronized shifts to keep their machines humming. The solution emerged not from astronomers or philosophers, but from the sweat and steel of the Industrial Revolution, standardized time zones. The shift began with Britain's Great Western Railway in 1840. Frustrated by scheduling nightmares, they adopted railway time, a single standard based on Greenwich Mean Time, enforced by synchronized pocket watches issued to conductors. Soon, station clocks displayed both local and railway time, their dual faces embodying the tension between nature and progress. By 1884, the International Meridian Conference formalized this system globally, dividing the world into 24 time zones centered on Greenwich. The telegraph, that era's internet, made synchronization possible. Time signals could now flash across continents in seconds, aligning clocks from Bombay to Boston with atomic precision. Factories became temples to this new mechanical time. Workers no longer followed the sun's rhythms or church bells, but the relentless pace of punch clocks and shift whistles. In textile mills, clocks were often placed high on walls out of reach, ensuring no one could tamper with the sacred schedule. Child laborers in Manchester's mills coined the term clocking in, their small fingers stained with oil from the machines they tended. Efficiency experts like Frederick Taylor even dissected workers' movements with stopwatches. Breaking tasks into fractions of a second time had become currency, measured and spent like coal or cotton. Yet this revolution sparked fierce resistance. Farmers protested that God's time was being replaced by corporate dictates, while railway workers grumbled about adjusting to artificial schedules. In one infamous 1883 case, a Cincinnati judge dismissed a lawsuit because the plaintiff used local solar time while the court followed railroad time. The very fabric of reality seemed to warp when standardized time reached Japan in 1886. Some villages reportedly hid their clocks rather than abandon ancestral rhythms. What's often forgotten is how deeply this reshaped human biology. The regimented 9-to-5 workday severed centuries of adaptation to natural light. Scientists now trace modern sleep disorders to this seismic shift. Our bodies still crave dawn to dusk cycles, but industry demanded we march to the beat of synchronized clocks. Today, when your smartphone automatically adjusts for daylight saving time, it's echoing a decision made not by nature, but by 19th century railroad barons who believed efficiency trumped the rising sun. The next time you check your watch, remember, those ticking hands carry the weight of an entire civilization learning to dance in perfect mechanical unison. Einstein's theory of relativity didn't just change physics, it rewrote humanity's entire understanding of time itself. Picture a Swiss patent clerk in 1905, scribbling equations that would unravel a truth hidden since the dawn of civilization. Time isn't a universal constant ticking the same for everyone. It's fluid, bending like rubber under the weight of gravity and stretching like taffy as you approach the speed of light. Newton had imagined time as an unwavering river flowing at the same rate everywhere, but Einstein revealed it as something far stranger, a dimension woven inseparably into the fabric of space, where clocks in motion tick slower than those at rest, and a person orbiting a black hole ages decades while their twin on Earth grows old. The implications were staggering. Suddenly, timekeeping wasn't just about measuring hours, it was about mapping the very geometry of reality. Einstein's equations showed that GPS satellites whizzing around Earth at thousands of miles per hour actually experience time slightly faster than clocks on the ground, gaining about 38 microseconds each day. Without correcting for this relativistic effect, your navigation app would misplace you by miles within minutes. Even the humble atomic clocks aboard these satellites, precise to within 1 second every 100 million years, must account for both their velocity and Earth's gravity warping space-time around them. But the real magic lies in how Einstein's insight connected time to the cosmos. His four-dimensional space-time isn't just a metaphor, it's the stage on which the universe performs. Massive objects like stars dent this fabric like a bowling ball on a trampoline, and just as a marble would spiral toward the ball, planets orbit stars because they're rolling along the curves of warped space-time. Time itself slows in these gravitational wells, an effect verified when atomic clocks placed at different altitudes tick at measurably different rates. Near a black hole's event horizon, this distortion becomes so extreme that time, from an outsider's perspective, appears to freeze entirely. What's often overlooked is how relativity touches our everyday lives. The electrons in your phone's processor move so fast that engineers must account for tiny relativistic effects to keep microchips synchronized. Particle accelerators like CERN rely on Einstein's math to prevent high-speed protons from arriving at collisions too early or too late due to time dilation. Even the aging of astronauts on the International Space Station, who return to Earth slightly younger than if they'd stayed ground-bound, proves relativity isn't just abstract theory. It's the silent architect of our technological world. Einstein's revelation humbles us. For all our atomic clocks and quantum chronometers, time remains a shapeshifter, reminding us that the universe operates by rules far wilder than our ancestors ever dreamed. The next time you check your watch, remember, those numbers aren't just tracking minutes. They're a fleeting glimpse into a cosmic dance where space and time twist together in ways we're only beginning to understand. Hidden deep inside laboratories around the world, machines no larger than a desktop printer tick with such precision that they redefine what it means to keep time. These aren't ordinary clocks, they're atomic chronometers, devices so accurate they could run for 15 billion years without gaining or losing a single second. At their heart lies a dance far more reliable than any pendulum or gear, the ceaseless vibration of cesium or rubidium atoms, oscillating with metronomic regularity under the gaze of lasers and microwaves. The magic happens when scientists isolate individual atoms in a vacuum, chilling them to near absolute zero to minimize interference. A carefully tuned microwave beam excites the atoms, causing their electrons to jump between energy levels at frequencies so stable they rival the rotation of planets. For cesium atoms, that magic number is 9,192,631,770 vibrations per second, a rhythm so consistent it was officially adopted in 1967 as the definition of the second itself. But atomic clocks do far more than just mark time. They form the invisible backbone of modern life. Every GPS satellite carries multiple atomic clocks because even a microsecond's error could throw off your location by hundreds of feet. Telecommunications networks rely on their precision to synchronize data packets racing across continents, while stock exchanges use them to timestamp trades down to the nanosecond. When scientists test Einstein's theory of relativity by comparing clocks on mountains versus valleys, or when astronomers track distant pulsars as cosmic timekeepers, they're standing on the shoulders of these quantum marvels. What's truly mind-bending is how these devices blur the line between science and philosophy. Atomic clocks prove that at the quantum level, time is astonishingly regular, yet relativity tells us it's also stretchable and warped by gravity. Some theorists now speculate whether time itself might emerge from deeper quantum processes, like temperature arising from atomic motion. The next generation of optical lattice clocks, accurate to within 1 second over the age of the universe, might soon test these wild ideas. Standing before an atomic clock, you're confronted with a paradox, a machine so precise it borders on the supernatural, yet one that reminds us how little we truly understand about the flow of moments we call time. It's both humanity's ultimate chronometer and a humbling symbol of the mysteries still ticking away beneath reality's surface. Today, time doesn't just tick, it pulses through our devices in relentless, glowing increments. With a glance at your smartphone, you can synchronize your schedule across continents, set reminders that chime like digital nagging, or even track your sleep cycles down to the minute. Yet this constant connectivity comes at a cost. Unlike our ancestors who shaped their lives around the rising sun or the harvest moon, we now live in a world where midnight emails and pre-dawn notifications blur the line between day and night, between work and rest. The same technology that grants us precision has also severed us from the natural rhythms that once governed human existence. Consider the paradox: we carry atomic clock accuracy in our pockets, yet our internal clocks, the circadian rhythms fine-tuned over millennia, are more out of sync than ever. The blue light from screens tricks our brains into thinking it's perpetual midday, suppressing melatonin and scrambling sleep patterns. Studies show that night shift workers, bathed in artificial light while the world sleeps, face higher risks of heart disease and diabetes. Even teenagers scrolling past midnight are unwittingly replicating the discord ancient societies feared, a life unmoored from the cosmic cycles that once dictated planting, prayer, and repose. This detachment from nature's tempo isn't just a personal struggle, it's a cultural shift with profound consequences. The always-on work culture, enabled by smartphones and globalized teams, means the sun never truly sets on productivity. A medieval farmer might have paused at dusk, but a modern freelancer can chase deadlines across time zones until exhaustion wins. The same tools that liberate us, letting us video call loved ones oceans away or stream a sunrise in real time, also tether us to a relentless artificial rhythm. Ancient sundials and water clocks reflected patience, their measurements bound to the pace of shadows and drips. Our digital clocks, by contrast, thrive on urgency, their milliseconds counting down to meetings, deadlines, and the next dopamine hit of a social media refresh. Yet echoes of the past persist. The rising popularity of digital detoxes and circadian lighting mimics the ancient quest for balance. Smartwatches now remind us to breathe or stand, much like monastery bells once called monks to prayer. Even the tech giants pushing perpetual connectivity are designing features to combat it: night modes, screen time reports, and focus settings that quietly acknowledge our need for boundaries. It's as if we're relearning what sundial carvers and candle clock makers knew instinctively. Timekeeping shouldn't just measure life, it should harmonize with it. Perhaps the ultimate irony is that our hyper-connected age has made us crave what our ancestors took for granted. The same apps that fracture our attention also offer guided meditations timed to lunar phases or sunrise alarms that gently rouse us with simulated dawn. In a world where time feels more fractured than ever, we're drawn back to the oldest truth of all, that time at its best isn't just counted, it's lived. For the Hopi people of the American Southwest, time doesn't march forward in a straight line. It spirals like the path of a hawk riding desert thermals. Their language holds no separate words for past or future, only variations of now, reflecting a worldview where ancestors and living generations exist in a continuous present. Imagine standing at the edge of the Grand Canyon, where layers of rock reveal epochs pressed together like pages in a book. This is how many indigenous cultures experience time, not as separate chapters, but as an ever-turning wheel where planting, harvest, and ceremony repeat in sacred rhythm. This cyclical understanding transforms how communities interact with the world, where Western calendars segment life into discrete blocks: quarters, fiscal years, deadlines. The Maori of New Zealand see time as the interplay of two forces: T-Core, the void of potential, and T-Po, the nurturing darkness. Their lunar calendar, Maramatoka, doesn't just track days. It prescribes when to fish, when to plant kumara, even when to hold difficult conversations, all aligned with the moon's energy. Similarly, the Yolngu people of Australia perceive time through songlines, ancestral paths sung into existence during the dream time, where walking the land becomes both navigation and a way of keeping creation's story alive in the present moment. The contrast with industrialized timekeeping couldn't be starker. Modern schedules treat time as a commodity to spend or waste, but for the Quechua farmers of the Andes, time is a relationship. Their agricultural cycles follow not just seasons, but the flowering of specific plants or the arrival of certain birds, a living calendar woven into the ecosystem. When a Quechua elder says, "The potatoes will tell us when to harvest," it's not metaphor, it's precision honed over millennia of listening to the land. Perhaps most radical is how these systems prioritize balance over progress. The linear arrow of time fuels our obsession with growth, but cyclical models embed limits. You wouldn't take more fish than the river can replenish, because next year's cycle depends on this year's restraint. The Diné Navajo concept of Hajo, often translated as walking in beauty, embodies this, framing time as a sacred loop where harmony between people, land, and cosmos must be continually renewed. These traditions aren't relics, they're lifelines. As climate change fractures industrial agriculture's predictability, scientists now study indigenous phenology, the observation of nature's timing cues, to adapt. When Sami reindeer herders adjust migrations based on lichen growth rather than fixed dates, or when Maori fishermen delay harvests until the pipi shellfish are fattest, they're practicing timekeeping as dialogue rather than domination. In a world racing toward exhaustion, their wisdom whispers an urgent question. What if time isn't a line to race along, but a circle to sustain? In 1947, as the world emerged from the shadow of nuclear war, a group of atomic scientists unveiled a timepiece unlike any other. A clock that didn't just tell time, but told humanity how much time it might have left. The Doomsday Clock, with its stark black and white face and ominous minute hand, became an instant symbol of the atomic age. Set at 7 minutes to midnight that first year, its creators meant every tick as a warning. This was no ordinary countdown, but a measure of how close civilization had crept to self-destruction. What began as a metaphor for nuclear threat has since expanded to include climate change, biotechnology, and cyber warfare, a proof that our reckoning with time has always mirrored our deepest fears. The clock's mechanics are deceptively simple. Maintained by the Bulletin of the Atomic Scientists, its time is set by a board of Nobel laureates and policy experts who weigh global risks like geopolitical tensions, carbon emissions, and emerging technologies. When the hand moves closer to midnight, as it did in 1953 during hydrogen bomb tests, or in 2020 when pandemic and climate crises collided, the world takes notice. But this isn't just scientific theater. The clock's power lies in its ability to compress complex threats into a single, visceral image. A farmer in Kenya and a senator in Washington can glance at the same dial and understand time is running out. What's often overlooked is how the Doomsday Clock inverts ancient timekeeping's purpose. Where Stonehenge or the Antikythera Mechanism sought harmony with cosmic cycles, this modern clock tracks disharmony, human actions pulling us further from stability. It echoes medieval apocalypse clocks in cathedrals, yet replaces divine judgment with cold data. The 23 times its hand has moved since 1947 trace our stumbles and progress like a heartbeat monitor for civilization. From the hopeful leap back to 17 minutes during Cold War détente to the unprecedented 100-second to midnight setting in recent years. The clock's true genius is its refusal to behave like a normal timepiece. It can stall for years, then lurch forward in sudden jumps, reflecting how risk accumulates beneath the surface until crisis erupts. Unlike atomic clocks counting perfect seconds, it acknowledges time as humans experience it, sometimes crawling, sometimes racing, always subjective. When climate scientists say we have 12 years to curb emissions, or AI researchers warn of near-term algorithmic dangers, they're speaking the Doomsday Clock's language, time as both measurement and ultimatum. Perhaps most haunting is how the clock makes abstract peril feel immediate. Midnight isn't a distant hypothetical, it's the hour after 11:59. The clock's designers understood something fundamental, that humanity responds to deadlines. Just as ancient solstice markers reminded tribes to store food for winter, this modern symbol prods us to act before the metaphorical seasons change. Its silent ticks ask a question as old as Babylon's star charts and as new as quantum computing. Will we use our time wisely, or let it slip through our fingers like sand in an hourglass? Floating 250 miles above Earth inside the International Space Station, astronauts witnessed something no ancient timekeeper could have imagined: a sunrise every 90 minutes. 16 bursts of daylight and darkness cycle past their windows each Earth day, turning the familiar rhythm of dawn and dusk into a disorienting strobe. Our bodies evolved across millennia to sync with a 24-hour spin of the planet, yet in orbit, circadian rhythms unravel like a broken clock. NASA scientists discovered that without artificial lighting mimicking terrestrial cycles, spacefarers' melatonin levels fluctuate wildly, disrupting sleep and cognitive function. The solution: an orbital compromise clock set to Greenwich Mean Time, matched to Mission Control's schedule, while LED panels bathe the station in wavelengths that trick human biology into believing in a steady sunrise and sunset. This cosmic time warp only intensifies as we reach for Mars. A day on the red planet lasts 24 hours and 39 minutes, just enough difference to throw off every Earth-bound clock, calendar, and sleep schedule. Imagine colonists setting watches to local, Sol time while their computers track mission elapsed time in Earth seconds, creating a temporal dissonance where birthdays arrive early and work shifts stretch longer each month. The challenge is so profound that scientists have proposed Martian time zones centered on prime meridians, while software engineers develop Sol's today's converters for mission planning. Even NASA Mars rovers operate on Martian time, with ground teams adjusting their sleep schedules by 40 minutes daily to stay synced with opportunity and curiosity, a practice so grueling it's nicknamed Mars lag. The deeper we venture into space, the more timekeeping transforms from practicality to existential puzzle. On the Moon, where a single day lasts 29 Earth days, future bases might adopt Lunar Standard Time, divorced from sunrises entirely. Interplanetary spacecraft like Voyager, now drifting beyond our solar system, carry clocks counting cosmic seconds since launch, a timestamp for any alien discoverers. And theoretical warp drives or wormholes could fracture time further, forcing navigators to account for relativistic time dilation across light years. These challenges eerily mirror those faced by ancient Polynesian navigators, who crossed oceans using star paths rather than clocks, or medieval monks recalibrating mechanical clocks for seasonal shifts. Once again, we're learning that time isn't absolute, it's a negotiation between place, physics, and perception. The second may be defined by cesium atoms, but as we leave Earth, we're forced to ask, does time belong to the universe or merely to the planet that first taught us to count its passing? At the cutting edge of laboratories where atoms dance to laser light, a new generation of clocks is emerging, machines so precise they could detect the faintest ripples in space-time itself. Quantum clocks, harnessing the bizarre behavior of particles like strontium or ytterbium, don't just measure time, they probe the fabric of reality. Picture atoms trapped in grids of laser beams, their electrons oscillating at frequencies 100 times finer than cesium's steady beat. These optical lattice clocks, as they're called, are so sensitive that placing one on a desk would make it tick slower than its counterpart on the floor, not because of mechanical error, but because Einstein's relativity dictates that time itself stretches under gravity's weight. What's truly staggering is how these devices could redefine our most fundamental units. The second, currently tied to cesium's vibrations, might soon yield to strontium's even more regimented rhythm, a shift akin to swapping a sundial for an atomic clock. But the implications go far beyond precision. Quantum clocks could one day form a planetary network, their synchronized ticks acting as a spiderweb to catch gravitational waves warping spacetime. Imagine detecting the aftershocks of colliding black holes not with sprawling observatories, but with discrepancies in clock times across continents. Yet the deeper mystery lies in what these clocks might reveal about time's origin. Some physicists now speculate that time isn't fundamental at all, that it emerges from some more basic layer of reality, like temperature arising from atomic chaos. In theories like loop quantum gravity, spacetime might be woven from discrete threads at scales a billion times smaller than an atom. If true, our perception of time's flow could be an illusion, a collective hallucination born from quantum interactions too minute for even these clocks to see. This quest mirrors ancient humanity's first attempts to grasp eternity. Just as Babylonian astronomers sought order in planetary cycles or Maya priests tracked celestial gears, modern scientists are decoding a cosmic metronome whose beats might unlock time's true nature. The difference: where our ancestors saw gods in the heavens, we're searching for equations, yet the ore remains unchanged. Every leap in precision doesn't just shrink our measurement errors, it humbles us with new questions. As we stand at this frontier, one truth becomes clear: timekeeping has always been humanity's way of conversing with the universe. From shadow clocks to quantum lattices, each device is a dialogue, an attempt to translate the cosmos' silent rhythms into something our minds can grasp. And perhaps that's the most profound legacy of all. Whether carved in stone or coded in lasers, our clocks are more than tools. They're mirrors reflecting our endless fascination with time's enigma, an enigma that, no matter how finely we measure it, never quite loses its mystery. Augustine of Hippo sat in his study in the 4th century, wrestling with a paradox that still baffles us today. "What then is time?" he wrote. "If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." This confession captures the central mystery. Time feels real as breath, yet slips through our fingers like smoke when we try to define it. Fast forward 16 centuries and philosophers remain divided. Some, like British idealist J.M.E. McTaggart, famously argued in 1908 that time is an illusion, a mere mental construct layered onto a static universe. His reasoning: events can be ordered two conflicting ways, either by sequence past, present, future, or by duration earlier, simultaneous, later, creating contradictions that suggest time isn't fundamentally real. But others push back fiercely. Physicists point to entropy, the irreversible increase of disorder described by thermodynamics, as proof time has an objective arrow. Watch milk swirl into coffee or a shattered vase fail to reassemble itself. These everyday miracles rely on time's one-way flow. Even Einstein's relativity, which made time flexible, didn't erase it entirely. It merely wove time and space into a single mutable fabric called spacetime. The debate splits along disciplinary lines. While quantum physicists grapple with theories where time emerges from deeper quantum processes, neuroscientists study how our brains construct the feeling of temporal flow through memory and anticipation. Cultures worldwide have mirrored this duality in their timekeeping. Ancient Hindu texts describe time as both linear kala and cyclical yuga, while Buddhist philosophy treats it as a conceptual overlay on timeless reality. Modern Western schedules treat hours as fixed blocks, but the Amazonian Amandawa people, who lack words for week or month, experience time as events tied to ecological rhythms, not abstract numbers. These differences aren't just linguistic quirks, they're lived experiments in whether time shapes reality or vice versa. Perhaps the most haunting evidence comes from those rare moments when time's illusion cracks. Patients under ketamine anesthesia report losing all sense of temporal flow, experiencing eternity in minutes. Near-death survivors often describe time collapsing, watching life events unfold simultaneously like cards fanned on a table. Even in daily life, trauma can distort time, seconds stretching into eons during a car crash, or childhood summers feeling longer than entire adult years. These glitches hint that our perception of time's river might be just that, a perception, not the river itself. Yet dismissing time as mere illusion feels equally unsatisfying. Farmers planting by moon phases or athletes timing split-second reactions rely on time's tangible effects. The wrinkles on our faces and the rings in tree trunks testify to its passage. Maybe the truth lies beyond the binary, time as both real and unreal, a fundamental property that our limited cognition filters into manageable chunks. Like fish unaware of water, we swim through time's currents, measuring its waves while still guessing at the ocean. In the quiet pre-dawn hours of a Hindu temple, priests perform rituals unchanged for millennia, their chants echoing through cycles of creation and dissolution known as yugas. Here, time isn't linear. It's a vast wheel turning through 4 ages, from the Krita Yuga's golden purity to the Kala Yuga's chaos, before the universe dissolves into primal waters and begins anew. This cosmic rhythm, stretching billions of years, offers something startlingly different from Western timelines. Not an arrow racing toward an end, but an endless dance where destruction seeds rebirth. The same philosophy pulses through Buddhism's wheel of samsara and Aztec myths of 5 suns, rising and falling cultures separated by oceans yet united in seeing time as a spiral staircase ascending toward enlightenment. Christianity, by contrast, imprinted the West with an eschatological vision time as a single, sacred arc from Genesis to Revelation. Medieval monks illuminating manuscripts drew world chronicles, mapping history from Eden to Judgment Day, every event a stepping stone toward divine fulfillment. This linearity birthed the modern idea of progress, but also a unique anxiety. If time has one direction, every moment becomes irrevocable. The Doomsday paintings of Hieronymus Bosch didn't just warn of hell. They crystallized a fear that clocks were counting down to salvation or damnation. Yet even within traditions, contradictions flourish. Judaism's liturgical calendar loops through annual Torah readings, while its prophetic books envision a messianic endpoint. Islam's Laylat al-Qadr, the night of power, holds that time folds in on itself yearly, allowing prayers on this night to transcend temporal limits. These aren't inconsistencies, but layered understandings, like a clock whose face shows both hours and seasons. Mythical ages mirror our deepest yearnings. Hesiod's golden age, where humans lived like gods, or the Norse Ragnarok's fiery renewal, reveal civilizations measuring time not in years, but in moral decline and redemption. The Hopi speak of worlds destroyed by human folly, each giving way to the next, a narrative chillingly echoed in climate change discourse today. What unites these visions is their power to transform time from measurement into meaning. When a Buddhist monk meditates on impermanence or a Christian prepares for Advent, they're not just tracking days, they're aligning their lives with stories that make eternity graspable. The next tick of your watch holds more than seconds. It carries the weight of every culture that ever looked to the stars and asked, "When do we belong?" Deep inside every cell of your body, a microscopic clock is ticking, not with gears or springs, but with proteins and genes that rise and fall in perfect 24-hour cycles. These circadian rhythms, Latin for around a day, are far more than just sleep schedules. They're the conductors of a biological orchestra, dictating when hormones surge, when muscles perform at their peak, even when our cells repair themselves. In 2017, 3 scientists won the Nobel Prize for unraveling this molecular machinery, showing how fruit flies with scrambled clock genes couldn't tell day from night, a discovery that revealed the same gears turn in human cells. Consider the ruthless precision of this system. Around 5 a.m., your liver begins stockpiling glucose, anticipating breakfast before you've even opened your eyes. By mid-afternoon, reaction times sharpen to Olympic levels, a leftover from when our ancestors needed peak alertness for hunting. Come evening, the pineal gland secretes melatonin like sand through an hourglass, gradually lowering body temperature and dimming mental alertness. These aren't suggestions, these commands written into our DNA over millions of years of evolution. Yet modern life wages silent war against these rhythms. Jet lag isn't just fatigue, it's your pancreas releasing insulin at the wrong time, your immune cells napping when they should be vigilant. Night shift workers, their circadian cycles perpetually out of sync with daylight, face higher risks of heart disease, diabetes, and even cancer. Studies show their bodies age faster, as if chronic misalignment grinds down telomeres, the protective caps on chromosomes. Hospitals now track chrono accidents, spikes in medical errors during pre-dawn hours when shift workers' alertness plummets. Ancient cultures intuited this connection long before microscopes. Ayurvedic medicine scheduled surgeries to lunar phases, believing blood clotting varied with cosmic cycles. Traditional Chinese medicine still maps organs to daily energy peaks. The livers shift from 1 to 3 a.m., the lungs at 3 to 5. Even Hippocrates noted fevers often broke at dawn, a phenomenon now explained by circadian regulated immune responses. The irony is profound. We've mastered atomic timekeeping, yet ignore the clocks built into our very cells. As chronobiologists drill deeper, they're finding these rhythms everywhere: in the opening of flower petals, the migration of monarch butterflies, even the reproductive cycles of plankton. Your body doesn't just keep time, it is time, a living echo of Earth's primordial spin. The next midnight snack or all-nighter isn't just breaking a habit, it's arguing with 4 billion years of evolution. Buried 40 feet beneath a college campus in Georgia lies a room unlike any other, a concrete vault sealed in 1940, filled with microfilm, seeds, and even a set of Lincoln logs. This is the crypt of civilization, the world's first modern time capsule, designed to remain sealed until the year 8113. Its creators didn't just pack away trinkets, they curated an entire era: newspapers documenting the rise of fascism, recordings of FDR's voice, even a specially constructed language integrator to help future linguists decode English. The message was clear: we were here, we mattered, and we wanted to speak across the chasm of time. This urge to reach beyond our mortal span is as old as civilization itself. The pyramids of Giza weren't just tombs, they were time capsules in stone, encoding pharaohs' names in hieroglyphs meant to endure forever. The Chinese Emperor Qin Shi Huang buried terracotta armies with precise astronomical alignments, ensuring his power would resonate through millennia. Even the Maya sealed jade artifacts beneath their temples, not for looters or archaeologists, but for gods and descendants they'd never meet. What unites these ancient efforts with modern projects like the Voyager Golden Record is the same aching question: how do you make a moment last when time itself is the ultimate eraser? Consider Voyager's golden disk, hurtling through interstellar space with greetings in 55 languages and the brainwaves of a lovesick teenager. Like the crypt's integrator, it includes a Rosetta Stone of pulsar maps to locate Earth across galactic time. But there's a heartbreaking irony here. The very technologies we use to preserve our legacy often become obsolete long before the message arrives. Would future humans recognize a vinyl record? Could they play the crypt's microfilm without a 20th century projector? The Navajo time capsules, woven into ceremonial blankets, patterns encoding generations of wisdom, might outlast them all precisely because they require no machinery, just living memory. Perhaps the most poignant time capsules are the accidental ones, when Pompeii's ash preserved a loaf of bread mid-bake or a dog forever straining at its chain. It captured mundane moments no one thought to memorialize. Similarly, the nuclear waste warning markers designed to last 10,000 years, featuring menacing earthworks and spike fields, may one day confuse more than caution. Will future civilizations see them as sacred barriers or puzzling art? The Ozymandias dilemma haunts every attempt to cheat time. Look on my works, ye mighty, and despair. What does this say about our relationship with timekeeping? That beneath the atomic clocks and quantum chronometers, we're still those same ancients carving notches into bones, desperate to say, we counted the days too. Whether etched in cuneiform or encoded in silicon, every time capsule is ultimately a sundial casting the shadow not of the sun, but of the fragile, brilliant minds that built it. From the first bone etchings tracking lunar cycles to the silent pulse of atomic clocks counting cesium vibrations, humanity's obsession with time has always been about more than mere measurement. It's a quest to pin down the invisible, to carve order from chaos, to whisper back to the universe, we see your patterns and we will learn your rhythms. The sundial's shadow, the water clock's drip, the pendulum's swing, each was a rebellion against time's relentless flow, an attempt to hold a mirror up to eternity. What's astonishing isn't just the ingenuity of these devices, but what they reveal about us. The Maya didn't just chart Venus to predict wars. They believed time was a living force, its cycles imbued with divine meaning. Medieval monks didn't merely invent mechanical clocks to mark prayers. They sought to synchronize human souls with celestial harmony. Even Einstein's Relativity, which shattered Newton's absolute time, replaced it with something more poetic, a cosmic fabric where past, present, and future intertwine like threads in a tapestry. Timekeeping, at its core, has always been an act of storytelling, and what stories these tools tell. The Antikythera Mechanism's corroded gears whisper of a Hellenistic world where science and myth danced together. The Doomsday Clock's ominous tick scream of an age haunted by its own power. The quantum chronometers humming in labs today, they're drafting the next chapter, one where time might not even be fundamental but emergent, a hologram projected from some deeper layer of reality we've yet to name. Yet for all our progress, we're circling back to ancient wisdom. Modern chronobiology confirms what Ayurvedic healers knew, that our bodies thrive when aligned with natural cycles. Digital detoxes echo the monastic retreats that once recalibrated human tempo. Even space agencies planning Mars colonies grapple with the same question sundial carvers faced. How do we harmonize with time when nature's cues vanish? So where does this leave us? With humility, perhaps? The same stars that guided Polynesian navigators now help calibrate GPS satellites, linking past and future in an unbroken chain. Every time you check your phone, you're touching the latest bead on that string, a thread spun from stone circles, water clocks, and atomic vibrations. The story of time isn't just about how we measure it, but how it measures us. Our ingenuity, our fears, our unyielding desire to find meaning in the tick and tock of existence. What's next? Maybe clocks that track quantum gravity, or calendars that sync with exoplanet orbits. Or perhaps we'll rediscover what sundial makers knew, that time's true magic lies not in controlling it, but in savoring our fleeting, precious place within its flow. The conversation's been going for 30,000 years. What will you add to it? Drop your thoughts below and keep exploring history's mysteries with us. The next chapter's always tick.